So in this example, we're given a simple network, and here we have a independent voltage source, V1, but then we have a dependent current source, which is dependent on the current flowing in this branch, Ix, and it's times some multiplier. So they're asking us to find V0 for the network shown. So to do this, we're going to do some nodal analysis. So let's look at how this works. So let's write our nodal equation, and we're going to do it for node A. And so this entire line up here is node A. So let's do that. And just to keep track, let's say this is node A equation. So if we look at the first branch, it's right here, and we're gonna arbitrarily say that current leaving the node is positive. So in this case, we're showing Ix going into the node, so it'll be negative. So that'll be a negative Ix. And then for our next branch out of here, we have the one with our current source, our dependent current source. So that one again is showing going into the node, so it'll be negative. So it'll be negative Kix. And then finally, we have our node with the voltage source. And so we're going to say that the current there from Ohm's law, so we remember that Ohm's law, V equals IR, but we can solve this for current, so it's I is equal to V over R, which V is the potential difference. So the potential difference here is, we'll say this one's leaving, so it'll be V0, which is this node here, minus V1, which is here, so it's V0 minus V1 is the potential difference, and is divided by this resistor RA. And so that's all the current that should be entering or leaving the node. So if we sum those up, then we should get 0, and we add those together. So another thing we're going to notice here then is right here, this component, the voltage across this component is V0, right? Because it's only one component, so it's the same as here. So we can again utilize Ohm's law. So again, V equals IR, but in this case, we're going to solve for I again. So in this case, I again is equal to V over R. So we'll have Ix as our I, V is V0, and R is RB. Again, that's utilizing this branch right here. That's just putting Ohm's law on that. So now we should be able to take this and substitute this in for our Ix's. So it's just a straight substitution. So let's do that. So when we do that, we will have negative V0 over RB. And then we'll have minus K V0 over RB. And then we will have plus V0 minus V1 over RA. And again, this is equal to 0. So now we need to solve for V0, because that's what they ask us to solve for. So the first thing we can do is we can subtract, we can multiply through by RA times RB, because that's what's in the denominator, one or the other in each one. So when we do that, we will get minus V0 RA, because the RB's cancel. Then we'll get minus K V0 RA. And then we'll get plus RB, because the RA's cancel out, times V0 minus V1. And so we can, and this all has to equal to 0. If we multiply the rest of this out, it's minus V naught RA minus K V naught RA plus RB V naught minus RB V1. Okay, so now, and this again equals to 0. So these terms have a V naught in them. This one does not, so we'll just add that to both sides. So and then we will factor out the V naught from these. So this will be V naught then times minus RA minus K RA plus RB, and that's going to be equal to V1 RB. And so finally, if we divide through by that amount on both sides, then we will have V naught is equal to V1 RB over RA minus RA times 1 plus K plus RB. So this is our equation for V naught, taking into account that we have a dependent current source.